Today we will begin looking at rates of change. To begin, the rate of change is the slope of a graph at a given point, where this point is A, F at A. So you can look below here. I've drawn already our secant and our tangent lines. Recall our secant is always our average rate of change. That is when we are using 2 points to look at the average rate of change, where our tangent is our instantaneous rate of change, where we're just looking at one point and looking at very, very close another point relative to that. So our average velocity here is equal to the change of position over our change of time. So therefore, our delta D over delta T is equal to our D2 minus D1 over T2 minus T1. We will now look at example 1. A pebble is dropped from a cliff with a height of 80 meters. After t seconds, it is s meters above the ground, where s at t is equal to 80 minus 5t squared, where t is between 0 and 4. Part A, we want to find the average velocity of the pebble between the times where t is equal to 1 and t is equal to 3. So we can find s at 1, which is equal to 80 minus 5 times 1 squared. Therefore, this will be equal to 75. And S3 is equal to 80 minus 5 times 3 squared, which is equal to 80 minus 45, which gives us a total of 35. We will now use these values to find our average velocity. Recall from before that our average velocity is equal to our change of position over our change of time. So we're going to take our average velocity is going to be equal to our S3 minus our S1 over 3 minus 1. Therefore, this will be equal to 75, oops, mistake there, I meant to say 35. 35 minus 75, all over 3 minus 1. That gives us negative 40 over 2. Therefore, that will give us negative 20 meters per second. Therefore, we have a negative slope. If we were to actually have a visual drawing of this, we would have our curve looking like this, where here would be our beginning value. We know about here would be 80, because this would be when our s value is equal to 1, and when our s value is equal to 3, that would be 35. Sorry, this should have been 75 there. This should have been 80, our beginning amount. And we will continue. In part B, we want to find the average velocity over 1 and 1.5 seconds. So from above, we found that s at 1 is equal to 75. And we now need to find what s at 1.5 is equal to. We sub 1.5 in for our x value, so we have 80 minus 5 times 1.5 squared. So this will be equal to 80 minus 11.25, which is equal to 68.75. So to find our average velocity here, we're going to take our change in our speed over our change in our time. So our s at 1.5 minus s at 1 all over 1.5 minus 1. So that will be equal to 68.75 minus 75 all over 0.5, which is equal to negative 12.5 meters per second. Now we ask ourselves, why are these velocities different? Well, if you recognize that the numbers in A are further apart from one another, where in B they get a little bit closer, so the actual slope, that change, is not as great. So the change in the change of position over the change in time is not as steep. So therefore, less of a slope. So let's just look at, when we are looking at these three values here on our time intervals, we can look at the average velocity. So if I were to sub these values in and find our average velocity, this would be equal to negative 10.5. Okay, and our next one, when t is between 1 and 1.01, this now is negative 10.05. And again, when t is between 1 and 1.001, our value of our average velocity is negative 10.005. So therefore, as the interval gets smaller, the average velocity approaches negative 10 meters per second. So therefore we know that the instantaneous velocity at 1, since we're looking at values that are very close to 1, is 10 meters per second. Sorry, negative 10 meters per second. Now let's look at the interval where t is between 1 and 1 plus h. So our average velocity here is going to be s at 1 plus h minus our s at 1. Because average velocity, we know we look at the change in our position, so our change in our speed over our change in time. So 1 plus h minus 1. So therefore this is going to be equal to s at 1 plus h minus s at 1 all over h. When we sub those values in, we get 80 minus 5 times 1 plus h squared minus 75 all over h. When we expand here, we have 80 minus 5 minus 10h minus 5h squared minus 75. Now, if you are forgetting how to expand, please go ahead and expand our 1 plus h squared and then multiply it by 5. But we should all be good at doing that by now. We will now collect our like terms, and when we do that, we're left with negative 10h minus 5h squared all over h. We're going to factor an h out so that we can get rid of our h in our denominator's position. So when we do that, we're left with negative 10 minus 5h all over h. Now these h values we know are going to cancel out one another, and then we are going to be left with negative 10 minus 5h. So therefore, that will be our average velocity. And when we're looking at as our h value would be approaching 0, the average velocity would be approaching negative 10 meters per second. So this is called the instantaneous rate of change, or just velocity. So therefore, the velocity of an object with position function s at t at time t equals a is equal to the limit of our change in position over our change of time. So we can do it the same way that we were doing our rate of our instantaneous our slope when we're finding our tangent. So note here that the velocity is the slope of the tangent to the graph s at t at point P, A, S at A, where our speed is our absolute value of our velocity. Recall that here, absolute value is when all values are positive. So example 2, we want to determine the velocity at 4 seconds of an object with position function s at t equals 10t squared minus 20t. So since we are looking at 4 seconds, we know that t is equal to 4. So therefore we're going to find what s at 4 is equal to. So when we sub in 4 into our values for t here, this will be equal to 160 minus 80, which is equal to 80. And our s at 4 plus h is equal to 10 times 4 plus h squared minus 20 times 4 plus h. When we expand this, this will be equal to 10 times 16 plus 8h plus h squared minus 80 minus 20h. When we expand even further and collect, we're going to be left with 80 plus 60h plus 10h squared. And since we're looking at our velocity at 4 seconds, we know that since we're not given 2 points, we'll be finding the velocity, which is instantaneous. So when we're doing the instantaneous velocity, we're always going to look at the limit as h approaches 0. So we're going to look at the limit at h approaches 0 of s at a plus h minus s at a all over h. And when we do this, we're just going to sub in our values. So 80 plus 60h plus 10h squared minus 80 all over h. When we collect our like terms and factor out, because we know that we have our 80s that are going to cancel out, so we can factor out an h from both terms in the numerator position, and we're left with 60 plus 10h all over h. So again, these h's will cancel out, and then we will be left with our limit as h approaches 0 of 60 plus 10h. So when we sub in that 0 there, we're going to just be left with 60. So always finish with a therefore statement. So therefore the instantaneous velocity at 4 seconds is 60 meters per second. And for our last example here, we're going to look at the total cost of manufacturing X units of a product by our C at X equals 10 the root of X plus 1,000. So in part A, what is the total cost of manufacturing 100 items of a product? What we're going to do with that 100? Does anyone know? Our 100 will be our X value. So therefore X is equal to 100. So all we need to do in part A here is sub in that X value into our given equation. So we will be having 100 times the square root, 10 times the square root of 100 plus 1,000, which is just equal to 100 plus 1,000, which is equal to $1,100. So therefore, $1,100 is the total cost to manufacture 100 items. In part B, it asks, what is the rate of change of the total cost with respect to the number of units X being produced when X is equal to 100? Again, since we are only given one value of X, we know that this is going to be an instantaneous rate of change. So again, we'll be looking at the limit as our H value approaches 0. So we can begin by looking at the limit at H approaches 0 of our C, because that was our given equation, 100 plus H minus our C at 100, all over our H value. So the limit as H approaches 0. So when we sub in for 100 plus h, we will have 10 times the square root of 100 plus h plus 1,000 minus 1,100 all over h. So we then can collect our like terms. So we can drop those brackets and have 10 times our square root of 100 plus h minus 100 all over h. Now recall from yesterday, we can never have an h value to be in the numerator position and it be negative, be 0. So what we need to do to get that h value out of our denominator position, we need to rationalize the numerator. So we're going to multiply by 10 times our 100 plus h plus 100. We're going to do this both to the top and bottom, so both to the numerator and denominator. And remember, this is just rationalizing. So when we do this, we're going to be left with the limit as h approaches 0 of 100 times 100 plus h minus 10,000. All over h times 10 times the square root of 100 plus h plus 100. So then we can expand, and when we do so, we are going to be able to cancel out our 1,000, because 100 times 100 will cancel out with that 1,000, and what we'll be left with is 100 h all over h times 10 times 100 plus h plus 100. And just like before, we can now cancel out those h values. So when we cancel out those h values, we're going to be left with the limit as h approaches 0 of 100 all over 10 times 100 plus h plus 100. So therefore, that's going to be equal to 100 over 200, which is equal to a half. We will see you guys tomorrow.